Hello Rustaceans, welcome to the 20th video of this Rust series. So today we will explore and get deep dive into the advanced features of Rust. So in previous video, we have covered the patterns and matching, and we have started a bit of the chapter 20. And as I have started opened the chapter 20.1, and we got stuck there because I thought that it will become more of a conceptual video and it will not digest easily for you. So I have thought that let's make that specific video smaller, keep that simple. So I have reduced that video to 1 hour and limited it to 1 hour 15 minutes. So now let's start with restart the concepts that we have started with in previous video. So in our previous video, um, we have covered the concepts of refutable, irrefutable, what irrefutable is. So these are the pretty much easiest concepts, and we have also covered the matching, match arms, what, why, and when the underscore can be used, the double dot can be used, how we can add the wildcards and add the wildcards in enums, structs, how to work with enums and structs within the match statements and patterns. So that's pretty much it. So let's get started with today's video and the topic advanced features. So we are on chapter 20th, chapter 20. So in chapter 20, the advanced features. So by now you have learned the most commonly used parts of the Rust programming language. Before we do one more project in chapter 21. So in chapter 21, we will build the multi-threaded backend or the web server. So we have already built that. We have built the backend application, the to-do application with Xsup. So if we will look at a few aspects of the language you might run into every once in a while, but may not use every day. But you can use this chapter as a reference for when you encounter any unknowns. The features covered here are useful in very specific situations. Although you might not reach for them often, we want to make sure you have a grasp of all the features Rust has to offer. In this chapter, we will cover unsafe Rust. So this is a pretty much great concept. So because Rust guarantees of some of the concepts like pointers about, let's say, so the Rust unsafe Rust does not mean that Rust will allow whatever you want to do with the Rust programming language. It means that it will allow you to bypass some of the compilers the restrictions so that you can work with any of the thing you want to do. So let's say you can, if you want to skip the compilation errors for dereferencing the pointers and so on and so forth. So you can do that. So how to opt out of some of Rust guarantees and take responsibility for manually upholding those guarantees. And then the second, advanced traits. There are two types of traits, associated types, default type parameters, sorry, multiple types, fully qualified, syntax, super traits. So these kinds of traits, let's say we have iterator trait, we have different kinds of traits. So how, in which category these default iterators fall in, and if I want to create my own trait, so how I can do that, and in which category it falls in. So fully qualified syntax, super traits, and the new type pattern in relation to traits. Advanced types, more about the new type pattern, type aliases, the never type, and the dynamically type size types. Advanced functions and closures, function pointers and returning closures, function pointers like simple functions, returning closures like, let's say we have a closure, and so this is what that means. So let's say dot map, and then we have a closure, and then we are returning that specific value, and we will deep dive into that later on. Macros, so ways to define code that defines more code at compile time. So we have, let's say, procedural macro. Uh, so so if you know about the macros that we usually do, let's say drive macro, debug macro. And if you want to create a separate macro rule, so how you can do that, so we will explore that in a while. So it's a panoply of Rust features with something for everyone. Let's dive in. So let's move on to the chapter 20.1. Unsafe Rust. All the code we have discussed, let me just quickly add. Yeah, this is perfect. All the code we have discussed so far has had Rust memory safety guarantees enforced at compile time. However, Rust has a second language hidden inside it that doesn't enforce these memory safety guarantees. It's called Unsafe Rust and works just like regular Rust but gives us extra superpowers. Unsafe Rust exists because by nature static analysis is conservative. When the compiler tries to determine whether or not code upholds the guarantees, it's better for it to reject some valid programs than to accept some invalid programs. Although the code might be okay, if the Rust compiler doesn't have enough information to be confident, it will reject the code. In these cases, you can use unsafe code to tell the compiler, trust me, I know that what I am doing. Be warned, however, that you use unsafe Rust at your own risk. If you use unsafe code incorrectly, problems can occur due to memory unsafety, such as null pointer dereferencing. Another reason Rust has an unsafe alter ego is that the underlying computer hardware is inherently unsafe. If Rust didn't let you do unsafe operations, you couldn't do certain tasks. Rust needs to allow you to do low level system programming, such as directly interacting with the operating system or even writing your own operating system. Working with low level systems programming is one of the goals of the language. Let's explore what we can do with unsafe Rust and how to do it. Unsafe superpowers. So to switch to unsafe Rust, use the unsafe keyword, then curly braces, and then you are good to go. And then start a new block that holds the unsafe code. You can take 5 actions in unsafe Rust that you can in safe Rust, which we call unsafe superpowers. Those superpowers include the ability to dereference a raw pointer. We will discuss about that. Call an unsafe function or method, access or modify a mutable static variable. What that means, I will explain it to you. Implement an unsafe trait, access fields of a union. It's important to understand that the unsafe doesn't turn off the borrow checker or disable any of Rust's other safety checks. If you use a reference in unsafe code, it will still be checked. The unsafe keyword only gives you access to these 5 features. So let's say if you have issues with the borrow checker, you have, let's say, issues in the borrowing, so it the Rust will warn you and the compiler will throw an error about that. So let's say, hey, there is an error on this line. You have, let's say, the ownership is moved out of scope and so on and so forth. So the error will be there. The borrow checker will run, the perform its duty and the responsibility. So only we have these 5 features we can work with, or Rust allows to access these 5 features with unsafe keyword or the unsafe block. You will still get some degree of safety inside of an unsafe block. In addition, unsafe does not mean the code inside that block is necessarily dangerous or that it will definitely have memory safety in problems. The intent is that as the programmer, you will ensure the code inside an unsafe block will access memory in a valid way. Um, People are fallible, and make mistakes will happen. But by requiring these 5 unsafe operations to be inside blocks annotated with unsafe, you will know that any errors related to memory safety must be within an unsafe block. So let's say if you want to manage the memory and you want to, let's say, work with dereferencing of raw pointers, so you should create an unsafe block and work with directly within that specific block. Keep unsafe blocks small, so let's say you can create multiple unsafe blocks there. You will be thankful later when you investigate memory bugs, so it will help you find the bugs, easily navigate to that error easily, because uh, so it's kind of similar thing. Let's say you can write your whole application in a single file, or whether you can divide your application into multiple components or separate files. So this is what they mean. You can write unsafe code in a single block, or you can create a separate blocks for each and every let's say feature or task you are working on. So let's say to isolate unsafe code as much as possible, it's best to enclose such code within a safe abstraction and provide a safe API, which we will discuss later in the chapter when we examine unsafe functions and methods, parts of the standard library, and are implement as safe abstractions over unsafe code that has been audited. Wrapping unsafe code in a safe abstraction prevents users of unsafe from leaking out into all the places that you or your users might want to use the functionality implemented with unsafe code, because using a safe abstraction is safe. Let's look at each of the five unsafe superpowers in turn. We will also so on. So now let's get deep dive into the dereferencing of our raw pointer. In dangling references in chapter 4, we mentioned that the compiler ensures references are always valid. Unsafe Rust has two new types called raw pointers that are similar to references. As with references, raw pointers is kind of similar to the references. Raw pointers can be immutable or mutable and are written as asterisks, const, and asterisk mute of raw pointers. Immutable means that the pointer can't be directly assigned to after being dereferenced. Immutable means that it cannot be assigned to any other variable uh, after the dereferencing, after it's being dereferenced. So different from references and smart pointers, raw pointers are allowed to ignore their, these are the rules, and these are the theoretical knowledge in that specific chapter. So I would rather suggest write down the major pointers, let's say, which I'm highlighting in the browser, so you can note that down somewhere and keep these pointers in mind, and you will uh, as soon as you start getting hands on it, you will get to know about the concepts much way better than you write on paper. Are allowed to ignore the borrowing rules by having both immutable and mutable pointers, or multiple mutable pointers to the same location, aren't guaranteed to point to valid memory, are allowed to be null, don't implement any automatic cleanup. By opting out of having Rust enforce these guarantees, you can give up guaranteed safety in exchange for greater performance or the ability to interface with another language or hardware where Rust guarantees don't apply. Shows how to create an immutable and immutable raw pointer. So it's it's a simple mutable variable, and now if you want to create a immutable or mutable raw pointer, so now how it can this can be done. So you are creating, assigning to r1 and raw const and num, and raw mutable and num. Const means it's immutable and mute means it's mutable, as name says. So notice the keyword says, sorry. Notice that we don't include the unsafe keyword in this code. We can create raw pointers in safe code. We just can't dereference raw pointers outside an unsafe block, as you will see in a bit. So you can create raw pointers outside the unsafe block. You don't need to have an unsafe block to create, let's say, raw pointers. Yeah, there must be an unsafe block when you want to dereference that specific raw pointer. So you must be careful that if I want to dereference a specific raw pointer, so I have to add an unsafe block, and I will move the code in that specific block, or will write that there. We have created raw pointers by using the raw borrow operators and person raw const num creates a Asterisk const means dereferencing I32 immutable raw pointer, and ampersand raw mute num creates a mutable I32 means the raw pointer. Because we created them directly from our local variable, we know these particular raw pointers are valid, but we can't make the assumption about just any raw pointer. To demonstrate this, next we will create a raw pointer whose validity we can't be so certain of using as to cast a value inside instead of using the raw borrow operators, and so on and so forth. So how to create a raw pointer to an arbitrary location in memory. Trying to use arbitrary memory is undefined. There might be data at that address, or might not. The compiler might optimize the code so there is no memory access, or the program might terminate with a segmentation fault. um, Usually, there is no good reason to write code like this, especially in cases where you can use a raw borrow operator instead, but it's possible. Why I'm reading the same wordings mentioned in the documentation? Because I'm thinking that it's a great way to explore the documentation and read out the necessary theoretical keywords so that we can remember them, learn them, and then we can hands-on practical implementation of that specific theoretical knowledge or the keywords applied. So let address is equals to, this is some kind of, you can say, the memory address, and r is equals to address as the raw pointer I32. It's the type aliasing. It's considered as the type aliasing, let's say, as to cast a value instead of using the raw borrow operator. So using as means to cast a value instead of using the raw borrow operator. So it means you are casting a value instead of using the raw borrow pointer. And let me explain it to you in a way. Recall that we can create raw pointers in safe Rust in safe code, but we can dereference raw pointers and read the data being pointed to. In listing 23, we use the dereference operator asterisk on a raw pointer that requires an unsafe block. Now here we have used the same code we have declared here, and now we are trying to dereference. Here we have created a raw pointer, and now here what we are doing, we are dereferencing. So asterisk means dereference R1 and dereference R2 means the dereferencing from a specific, let's say, memory block. Creating a pointer does no harm. It's only when we try to access the value that it points at that we might end up dealing with an invalid value. Note also that in 21-23 we created const 32 raw pointers, and both pointed to the same memory location where num is stored. If we instead tried to create an immutable and a mutable reference to num, the code would not have compiled, because thus ownership rules don't allow a mutable reference at the same time as an immutable reference. If I want to try it inside, let's say, in a Rust program without an unsafe block, let me just remove it from here. Let's just copy this and let's just create a project. Check. All right, let me just create a project here. All right, so I have created a new project with a command cargo new and the lecture 18. So let's say paste the code that I have copied from the documentation. Let's save it really quick and run the command cargo. All right, R1 is 5, R2 is 5. We are assigning the raw pointer to the R1 and the R2. The variable is same for both of them. So what if I want to dereference both of these in without an unsafe block? So how we can do that? Let's just save it really quick. Let me see what we are getting here. Terminal, save it. So the extensions are loading here. So let's just skip formatting here and let's just run the command cargo run. So here you can see dereference of a raw pointer. Dereference of a raw pointer is unsafe and requires unsafe block. So you cannot dereference a raw pointer from within without an unsafe block. So you have to use an unsafe block to dereference a raw pointer, same as we already covered. So let's just quickly go to the documentation and calling an unsafe function. One more thing. With all these dangers, why would you ever use raw pointers? One major use case is when interfacing with C code, as you will see in the next section, calling an unsafe function or method. Another case is when building up safe abstractions that the borrow checker doesn't understand. We will introduce unsafe functions, and then so let's say if you want to get an abstraction of C code. So usually when working with the systems programming, you uh, get some kind of you might have some kind of use case to work with raw pointers. So you have to access that you have to access the memory specific memory block. And so what you have to do, you have to add an unsafe block and work with C directly. So you have to add some kind of macros there and so on and so forth. So I'll explain it to you now by calling an unsafe function or method. The second type of operation you can perform in an unsafe block is calling the unsafe functions. Unsafe functions and methods look exactly like regular functions and methods, but they have an extra unsafe before the rest of the definition. So what we usually do, we usually add an unsafe block inside whatever thing we are working. So let's say if we are working on main function or in any function, we used to directly declare the unsafe block there. However, if I want to uh, work with, let's say, unsafe functions, so what unsafe functions means, add an unsafe keyword before defining any function. So let's say unsafe function and main. Unsafe function, let's say function name is palindrome. Make, let's say, let's say there is a function name called as make palindrome. So we can add the unsafe block beforehand to access the unsafe features, but they have an extra unsafe before the rest of the definition. The unsafe keyword in this context indicates the function has requirements we need to uphold when we call this function. Because Rust can't guarantee we have met these requirements. By calling an unsafe function within an unsafe block, we are saying that we have read this function's documentation and we take responsibility for upholding the function's contracts. So let's say if you are using an unsafe keyword before your function declaration or definition, so what you have to do? So first of all, let's understand what it means. So you are saying to Rust, consider Rust is as a person. So you are saying to Rust that I have read the documentation and I know what I am doing and I know the repercussions of that specific implementation. I know the pros and cons. So Rust will say, okay, perfectly fine. You so just add the keyword unsafe and then you are good to go. That's pretty much it. This is the simple concept. Here's an unsafe function named dangerous that doesn't do anything inside in its body. Right now, it doesn't do anything. So now it's called to unsafe function here. So now why there is an error? Because with the unsafe block, we are asserting to Rust that we have read the functions documentation, we understand how to use it properly, and we have verified that we are fulfilling the contract of the function. To perform unsafe operations in the body of an unsafe function, you still need to use an unsafe block just as within a regular function, and the compiler will warn you if you forget. This helps to keep unsafe blocks as small as possible, as unsafe operations may not be needed across the whole function body. So here you can see call to unsafe block, consult the functions documentation for information how to avoid undefined and so on. Creating a safe abstraction over unsafe code. Just because a function contains unsafe code doesn't mean we need to mark the entire function as unsafe. So let's say uh, there is a specific piece of uh, code inside the function, so you don't need to make this whole specific function as an unsafe. You should not mark the function as unsafe, and so you can create a separate block within a function. No worries about that. In fact, wrapping unsafe code in a safe function is a common abstraction. As an example, let's study the split at mute function from the standard library, which requires some unsafe code. We will explore how we might implement it. This safe method is defined on mutable slices. It takes one slice and makes it two by splitting the slice. So let's just review the code. This is a pretty much a simple I32 vector mutable. And now here I'm referencing this specific v as a vector, so I'm assigning it to r. R is the reference to that specific v vector. R dot split at mute 3, so it will split at third position, so 1 2 3 will be splitted and 4 5 6 will be splitted. We can implement this function using only safe rust. Any attempt with attempt might look something like listing 25, which won't compile. For simplicity, we will implement a split at mute as a function rather than as a method, and only for slices are 32 values rather than for a generic type p. So you just only have to use it with I32. Don't You cannot use with generic type. So let's say if split at mute, so on and so forth, it will return the mutable, it's the tuple length values dot length assert if the middle less than is equals to length, and so on and so forth. So here you can see an error. First mutable borrow occurs here, second mutable borrow occurs here. Dot split at mute position to obtain two mutable non-overlapping sub-slices. Let's call the function the lifetime of this reference I. So now here you can see if I want to pass anything to that specific function, because um, dot split is I'm considering dot split as a method, not as a function. So if I want to create a separate function here, so split at mute is a separate function. If I want to get the tuple from here, so I can do that directly. So now here you can see split at mute is a separate function. Inside that length pointer as mute pointer, I'm referring getting the mutable pointer, and then slices from raw parts mute pointer mid, and I'm passing the pointer to the current value and the mid, and then pointer dot add mid at the middle value length minus mid, and separate. Simple as that. All right, so recall from the slice type in chapter 4 that slices are a pointer to some data in the length of the slice. We use the len method to get the length of a slice, and the as mute pointer method to access the raw pointer of a slice. You will get the raw pointer of that specific slice. In this case, because we have a mutable slice to I32 values, as mute pointer returns a raw pointer with the type like asterisk mute and I32, which we have stored in the variable ptr means pointer. We keep the assertion that the mid index is within the slice. Then we get to the unsafe code, and the slice from raw parts mute function takes a raw pointer and a length, and it creates a slice. We use it to create a slice that starts from pointer and is mid items long. Then we call the add method on pointer with mid as an argument to get a raw pointer that starts at mid. So here we are getting the pointer of a slice and the middle value, which is considered as within a slice, the reference to the that specific slice. uh, Slice from raw pointers, and we are adding the middle value inside that pointer. Then we call the add method on pointer with add mid as an argument to get a raw pointer that it starts add mid, and we create slice using that pointer and the remaining number of items after mid as the length. This function slice from raw parts mute is unsafe because it takes a raw pointer that and must trust that this pointer is valid. The add method on raw pointers is also unsafe because it must trust that the offset location is also a valid pointer. Therefore, we had to put an unsafe block around our calls to slice from raw pointers and add so we could call them by looking at the code and by adding the assertion that must be less than 2 equal. So it's pretty much simple that what we are doing, we are getting the pointer of uh, we are referencing to the, let's say, vector v, where we have a length of the vector of I32, and then we are referencing, or we are creating a pointer by referencing to that specific variable. So, and then we are created two different functions, from mute pointer, and then from mute pointer mute, from raw parts mute, and then we are getting the values after that specific middle part. In contrast, the use of slice from raw parts mute in listing 27 would likely crash when the slice is used. This code takes an arbitrary memory location and creates a slice 10,000 items long. Here, we are importing the slice from standard library, address to that, let's say, memory, address as means casting, and then the raw pointer, and then values unsafe blocks from parts mute, and the R 2000. This what 1000 means? It's creating a slice 10,000 items long. That's the issue because it will get crashed. We don't own the memory at this arbitrary location, and there is no guarantee that the slice this code creates contains valid I32 values. Attempting to use a value attempting to use values as though it's a valid slice results in undefined patterns behavior. Now, I have uh, told you that we will see that we can use the C code inside our Rust program. So how we can do that? We can use with the keyword extern. So let's say pub extern and then so on and so forth. So we can define the function name and then the extern keyword and then so on and so forth. So sometimes your Rust code might need to interact with code written in another language. For this, Rust has the keyword extern here that facilitates the creation and use of foreign function interface FFI. And FFI is a way of for a programming language to define functions and enable a different foreign programming language to call those functions. It's kind of a barter system from which means that you are using the functionality or code of that um, of another language in your Rust program. This demonstrates how to set up an integration with the absolute function ABS from the C standard library. Functions declared within external blocks are generally unsafe to call from Rust code, so external blocks must also be marked unsafe. It must be marked as unsafe. Rust by default don't mark it unsafe. Rust can't check them, so responsibility falls on the programmer to ensure safety. Unsafe extern C, and then you are using a function absolute I32. Main unsafe print absolute value of -3 according to C absolute -3. So let's say if I want to use it in my Rust code, let's just implement it really quick. Go in the lecture 18. And here, let's just comment all the stuff here. And let's just remove the main function from there and this main outside. So now it will print this line, absolute value of minus 3 according. Run the cargo run command. And yes, absolute value of -3 according to C is +3. So it's coming from the C programming. Let's just go back to the documentation and stable. Unsafe Rust, and here we are within the unsafe extern C block. We list the names and signatures of external functions from another language. We want to call the C part defines which application binary interface, the ABI. If you will work on the smart contracts, the blockchain development, you will majorly hear about the ABI, what ABI is. So we will talk about this in a while. The external function uses the ABI defines how to call the function at the assembly level. The C ABI is the most common and follows the C programming language ABI. Information about all the ABIs Rust supports is available in the Rust reference. Let's just click on this link and go back to the, let's navigate or uh, to the external blocks. And here you can see the ABI. By default, external blocks assume that the library they are calling uses the standard C ABI on the specific platform. So you can, how you can use this ABI in your Rust program. So here you can see. So we have, let's say, cortical default x8632 C code, STD call for Windows 32 API, and there are multiple bunch of multiple other specific APIs. So let's say if I want to work with ARM, so you can say AAPCS. And then this is pretty much safe. And here, when every item declared within an unsafe external block is implicitly unsafe. However, some FFI functions are safe to call. For example, the absolute function from C's standard library does not have any memory safety considerations, and we know it can be called with any i32. And one more thing. So here you can see if the Rust by default marked as unsafe. However, it's nothing to do with it's not working with raw pointers. It's not indicating that it's working and accessing any unsafe features. So by default, any function within an extern uh, block, Rust marks this block or all the function inside that block as the unsafe. So if I want to mark any function as safe block, so let's say, hey Rust, this is not an unsafe block. It's nothing to do with that. So I can add a safe keyword and it will consider it as the safe function. So you can work with that and Rust will check or compile that. Oh, compiler will check the errors on that. Uh, and here we are calling Rust functions from other programming languages or the other languages. We can also use extern create to create an interface that allows other languages to call Rust functions. Instead of creating a whole extern block, we add the extern keyword and specify the ABI to use just before the function keyword for the relevant function. We also need to add an hashtag or the macro unsafe no mangle annotation to tell the Rust compiler not to mangle the name of this function. Mangling is when a compiler changes the name we have given a function to a different name that contains more information for other parts of the compilation process to consume it, but it less human readable or readable. Every programming language compiler mangles names slightly different. So for a Rust function to be nameable by other languages, we must disable the Rust compiler's name mangling. So it's considered, so let's say to disable anything. So let's say if I want to disable that Rust compile, so that the other programming language cannot identify that, let's say what this function is. So let's say call from C. So we are mentioning that no mangle means it's not about the C, you can say. So every programming language compiler mangles names slightly differently. So for a Rust function to be nameable by other languages, we must disable the Rust compiler's name mangling. This is unsafe because there might be name collisions across libraries without built-in mangling. So it is our responsibility to make sure. So let's say if I want to add the no mangle block, and if you want to add a function absolute here, so there is an error. In the following example, call from Rust function accessible from C code after it's compiled to a shared library and linked from the C. So let's say, let's copy that specific code block. Okay, so let's say cargo run. Here, absolute value of -3 according to C and 3. So we are attribute should be applied to a free function, impl method or static. This was previously accepted by compiler, but it's being phased out. It will become a hard error in a future release. So let's say how we can do that. We can pub extern C, and then we have to directly use this function here. Let's say, and we can add the functionality inside that. If I want to, let's say, add the functionality here, print ln hello. Here is an error, doesn't implement the fmt cargo run hello and the absolute value of -3 according to C. Hello is printed here, and then this code block. Now, this usage of extern requires unsafe only in the attribute, not on the extern block. Accessing or modifying a mutable static variable. What does this mean? Static means the specific keyword which will remain same in throughout your program. So, how to modify a static variable? So let's get into it, or let's just review it. We have not yet talked about the global variables which Rust does support but can be problematic with Rust ownership rules. If two threads are accessing the same mutable global variable, it can cause a data race. All the concepts that we have covered in previous videos, so you can recall that. In Rust, global variables are called static variables. Listing 2010 shows an example declared and use of a static variable with a string slice as a value. So this means that hello world hello world variable will remain same throughout the application. If I want to make it mutable or make changes to that specific variable, how I can do that? Let's just review. Static variables are similar to constants which we discussed in constants in chapter 3. The names of static variables are in screaming snake case by convention. Make it, let's say, uppercase and add the underscores between, let's say, for separations. Static variables can only store references with the static lifetime, which means the Rust compiler can figure out the lifetime and we aren't required to annotate it explicitly. Accessing an immutable static variable is safe. Alright, sorry for that. A subtle difference between constants and immutable static variables is that value in a static variable have a fixed address in memory. Using the value will always access the same data. Constants, on the other hand, are allowed to duplicate their data whenever they are used. Another difference is that static variables can be mutable. This is the major point. Static variables can be mutable through, let's say, before this chapter, we were thinking about these static variables will remain same throughout the application. So how I can modify that? So let's just accessing and modifying mutable static variables is unsafe. It's unsafe. First thing, shows how to declare access and modify a mutable static variable named counter. So static, add the keyword mute counter, and safety calling this from one more than a single thread at a time is undefined behavior. So you must guarantee you only call it from a single thread at a time. So let's say, if I want to update a static variable from multiple threads at once, this is major thing. At once means I'm updating a static variable all at once, at a single time, and it might throw um, as undefined. behavior. So Rust does not support the undefined behavior. So Rust says type save, memory save. So this is an error. So we have to manage it by ourselves, that we will only call, or we will only update a static variable at s- from a single thread at once. So let's say if I'm updating a static variable in multiple threads, but they are running, let's say first thread will run, first thread is running at first, and then second thread is running after 2 seconds. So its first code block has run its implementation, the static variable is updated, and then it's started to update. So there is no worries about that. You can update that. Unsafe function add to count, unsafe counter plus equals to included. Safety, this is only called from a single thread in main function add to count, and then the println function. As with regular variables, we specify mutability using the mute keyword, and they are explaining everything from there. And then unsafe trait. We have already covered that unsafe static variables, unsafe trait, unsafe extern if I want to access the functionality from from other languages. And so this is the second last of that. We can use unsafe to implement an unsafe trait. A trait is unsafe when at least one of its methods has some invariant that the compiler can't verify. We declare that a trait is unsafe by adding the more unsafe keyword before trait and marking the implementation of the trait as unsafe too. So, as shown in listing 20, unsafe trait method goes here, unsafe implementation of that specific trait. By using unsafe implementation, we are promising that we will uphold the invariants that the compiler can't verify. As an example, recall the sync and send marker traits we discussed in extensible concurrency. In chapter 16, the compiler implements these traits automatically if our types are composed entirely of other types of that implement. So let me just open that. And here you can see trait send is not implemented for reference counted pointer, mutex, and the I32. So here, um, yeah. So here they are saying that trait is not implemented. When we switch to arc, the atomic reference pointer, which does implement send, the code compiled. So we have had to use the arc to compile the code. If we implement a type that contains a type that does not implement send or sync, such as a raw pointer, and we want to mark that type as send or sync, we must use unsafe. Rust can't verify that our type upholds the guarantees that it can be safely sent across threads or access from multiple threads. Therefore, we need to do those checks manually and indicates as such with unsafe. So now accessing fields of a union, the final action that works only with unsafe is accessing fields of a union. A union is similar to a struct. Let's see, but only one declared field is used in a particular instance at one time. So you can declare one field in one instance, let's say. Unions are primarily used to interface with unions in C code. Accessing union fields is unsafe because Rust can't guarantee the type of the data currently being stored in the union instance. You can learn more about unions because R- Rust says that you have to be careful that if you are updating anything multi at let's say if you want to update variable multi, at multiple in multiple, let's say, instances or multiple code blocks, so you cannot do that. So the result might so let's say the first thread, second thread, and third thread, all three of them are updating a single variable. So there would be a data race. So the first one will get some other data, it will get some other data, third one will get some other value, and there will might be a data race and the program will crash. So Rust makes you or force you that don't do this specific operation. And union, so here is an example: union, my union, f1 u32, and then you have to so initializing u my union and unsafe, and you want to access that, let's say, value. So u dot f1, the expression above, creates a value of type my union and initializes the storage using field f1. The union can be accessed using the same syntax as struct field, so same as we usually do with the structs, and reading and writing and then so on and so forth. This is pretty much simple. And using Miri to check unsafe code. When writing unsafe code, you might want to check that what you have written actually is safe and correct. One of the best ways to do that is to use Miri, an official Rust tool for detecting undefined behaviors. So you have to run this command cargo nightly Miri run, and then it will install this tool, an official Rust tool for detecting. And whereas the borrow checker is a static tool that works at compile time, Miri is a dynamic tool that works at runtime. It checks your code by running your program or its test suite and detecting when you violate the rules it understands about how Rust should work. And then using Miri requires a nightly build of Rust. And one more thing. So there are three steps of when the Rust uh, creates its new version or release its new version. So let's say there is a weekly release, the weekly version upgrades, then monthly version upgrades, the daily upgrades, and so on and so forth. So uh, you can see when to use unsafe code. Using unsafe to use one of the five superpowers just discussed isn't wrong or even frowned upon. But it is trickier to get unsafe code correct because the compiler can't help uphold memory safety. When you have a reason to use unsafe code, you can do so, and having the explicit unsafe annotation makes it easier to track down the source of problems when they occur. Whenever you write unsafe code, you can use Miri to help you be more confident that the code you have written upholds Rust rules. For a much deeper exploration, you have to effectively with runs. Consider Rust, read Rust official guide to the subject, the Nomicon. This is a separate documentation. The dark arts of unsafe Rust, and we will explore it later on. So let's just quickly go to the next chapter. All right, so advanced traits. And before moving forward, let's just install the Miri in your terminal. So run the command rust up component add minus minus toolchain nightly minus 86 x 86 86 by 64 bits of your, if you are using 64-bit PC, unknown Linux GNU, and then Miri, and it's downloaded. And if you want to run the cargo nightly Miri run, so it will work perfectly. I will run the rest up. Yes, and it will run install the necessary components. Till then, we will explore the documentation. So advanced features, we first covered traits and traits defining in chapter 10, but we didn't discuss the more advanced details. Now that you know more about Rust, we can get into the nitty gritty. Associated types connect a type placeholder with our trait such that the trait method definitions can use these placeholders types in their signatures. The implementer of a trait will specify the concrete type to be used instead of the placeholder type for the particular implementation. That way, we can define a trait that uses some types without needing to know exactly what those types are until the trait is implemented. So this is pub trait iterator, the default iterator trait So one example of a trait with an associated type is the iterator trait that the standard library provides. The associated type is named item here, and it stands in for the type of the values the type implementing the iterator trait is iterating over. The definition of the iterator trait is as shown in, we have already seen that in our previous videos that when working with the iterators. So here we are defining the type item. So what type item is? Item refers to the type of that specific item and so on. So let's say the type item is a placeholder, and the next method's definition shows that it will return values of type option self item. The item is the placeholder type. So implementers of the iterator trait will specify the concrete type for item, and the next method will return an option containing a value of that concrete type. Associated types might seem like a similar concept to generics. So in that later allow us to define a function without specifying what types it can handle. To examine the difference between the two concepts, we will look at an implementation of the iterator trait on a type named counter that specifies the item type. So they have implemented the item as U32, and then pub trait, they have added a generic here, and then so this is considered the similar concept as we have in generic. So let's say we can pass the generic and then we can return the type here. So why not just define the iterator trait with generic? So there is a question that why not you can add a generic type here and then just return the generic from there instead of adding a placeholder type here. So the difference is that when using generics as in 2014, we must annotate the types in each implementation, because we can also implement iterator string for counter or any other type. We could have multiple implementations of iterator for counter. In other words, when trait has a generic parameter, it can be implemented for a type multiple times, changing the concrete types of the generic type parameters each time. When we use the next method on counter, we would have to provide type annotations to indicate which implementation of iterator we want to use. With associative types, we don't need to annotate types because we can implement a trait on a type multiple times. With the definition that uses associated types, we can choose what the type of item will be only once, because there can only be one implementation iterator for counter. So it's the matter of the repetition of same type. So let's say I'm redefining the traits with multiple types, with multiple traits, or the multiple types can be considered as. So it's just the matter of types definition and the repetition or redeclaration of that block. Associated types also become part of the traits contract. Implementers of the trait must provide as type to stand in for the associated types placeholder. Associated types often have a name that describes how the type will be used, and documenting the associated type in the API documentation is a good practice. So for this, we can also let's just do an hands-on implementation of the generics. We are on lecture 18, so it's working perfectly fine. Let's just remove that and let's just do one thing. Let's just take the same example as given in the documentation about, let's say, iterator, and let's just see what's the difference between the generic and the uh, item or the item, like the static type here. So what does this mean? So associated types, this is considered as the associated type. So the syntax would look like same. So let's say um, we have, let's say, trait of iterator, and inside that we can, let's say, here let's say we have, let's say, type item and then function. So let's just copy it and let me just explain it to you. And so what if I have a struct here counter and counter, and let's just keep it as empty for now. And implementation of counter, the iterator for counter, and inside that, because we have the is equals to type is equals to, let's say I have, oh, item is equals to, let's say I want to pass the ith32, so I can pass the ith32 type, and the function next would be, let's just copy it, and the implementation will remain same. However, if I want to add an other implementation with another type, so let's say if I want to pass the implementation with u16 type, so and let me save it. So here you can see an error here. Let me just, okay, so because I haven't returned anything, so there is an error for that. So let me just quickly go to the documentation and get this something. Let's just get the implementation from here. So let's say, because we have an option, so let's just pass the sum and some value here. And let's just save it, and let's see what we have. Conflicting implementations of trade iterator for type counter, conflicting. So we are conflicting the implementations for the iterator traits. But one more thing. Here, first implementations is here, and the second implementations we have declared here. So let's say if I pass the type U32, and then, so let's just save it really quick. And then what does this mean? That I cannot pass, because the item type, the type item would be would remain same in all the implementations. And with, let's say, generics, so let's just copy the implementations of the generic here from here. So pub trade iterator and the generic trade. So now I can pass multiple implementations of the iterator trade with different types. So let's say first type will be U32, then second type will be U16. You can pass whatever implementations with whatever type you want. So let's go back to the documentation and continue with the okay, the default generic type parameters and operator overloading. When we use generic type parameters, we can specify default concrete type for the generic type. This eliminates the need for implementers of the trait to specify a concrete type. If the default type works, you specify default type when declaring a generic type with the placeholder type and the concrete type syntax. And then Rust doesn't allow you to create your own operators or overload arbitrary operators, but you can overload the operations as corresponding traits listed in standard library operations, or the operators, by implementing the traits associated with the operator. For example, we overload the plus operator, or to add 2 point instances together, we do this by implementing the add trait on a point. So let's say we are importing or using the add operator, and then we are creating a struct with, let's say, struct point, and then implementing the add for point, and then we are passing the point to the output. So this means that we will return the point. The point means the struct from the add implementation rather than the simple add operation. So what we have, let's say, let me just quickly copy this code, and let's just uh, comment all these stuff. So let's say we are here, and let's just save it really quick and save it and go to the add. Let's open the file add, and inside that we have the right hand side is equals to self and the resulting, and the the type is output, and then this is not a generic type. This is the type output, which is as an associated type, which is needed to be returned from this function add. And now here, what I'm doing, I'm overriding or overwriting that specific add function, and I'm doing, I'm returning a point. Point is a struct which I'm returning from this add function, and what I'm doing, I'm adding the x and x, the self x, the incoming x from the specific add trait, and then the other will come from the point other dot x and the other dot y. So this is pretty much simple, and let's just go back to the documentation, and then they are explaining everything in there. You will use default type parameters in two main ways. To extend a type without breaking existing code, there are two choices. To allow customization in specific cases most users won't need. You can customize it, you can extend the code. Uh, if you can remember or the recall the example from the OOP, this is not similar kind of example, but the concept is same. Uh, about the inheritance. Inheritance means you inherit the implementation from the parent component. In the first type, you are extending the implementation, extend that type without breaking the existing code. So that's pretty much it. So let's read out the or understand what's disambiguating between methods with the same name. All right. So in this chap or in this topic, it means that disambiguating between methods with the same name. So in this, let's say I have multiple traits with the same methods. The method name would be same. So how we can work with that? How we can call? Let's say I have a. Let's take an example here. We have a trait pilot here with a method fly, wizard with a method fly, and we are implementing the struct human with implement pilot, and we have another let's say function fly, and then we are implementing human. Simple is that we are adding a separate method for that as waving arm. So let's say, let's just copy that code and let's just try to implement this. And let's say, so how we can call any specific function. Let's just quickly move this here. Mhm. Yeah, perfect. Fine. Let's just save it. And what if I want to call, let's just first call this fly function and if I want to print this waving arm furiously. So how we can do that? Let's just quickly let person is equals to, and then we can create, let's say, human struct, and inside that human struct we don't have anything here, so we can just implement or add the semicolon, and inside that, let's say I want to call the fly method. So let's say fly dot, and let's call this fly method, and what let's see what it prints out. Cargo run, whether it prints run this fly function or this fly. So let's say so waving arms furiously. So it's running this fly method implemented on struct directly. So what if I want to print, let's say, the fly method or run this fly method implemented on wizard. So how I can do that? I can do, let's say, I can run, let's say, person dot and or person. Okay, wait. Let's say we have wizard. So inside that wizard, we have a function called as fly, and inside that we have to pass the reference to that self. So self means the self as a human struct. We have implemented the human instruct on the wizard. So let's just quickly save it and then run the command cargo run. So now it will print the fly method implemented on the wizard trait. So here you can see the up and then waving arms furiously. And then there's one more thing. instead of implementing, let's say, person dot fly and wizard fly, I want to, let's say, I want to print like that. So I want to print fly method directly without explicitly mentioning that, hey, go to the wizard implementation and then use the fly method and pass the self. Instead, what I can do, let's just remove the self from all this implementation, all these implementations. Let's just quickly remove self. And now if I run this command human and fly, what it will do, it will print out the it will run the default fly method waving arms furiously. So what if I want to print this function, this fly up? How I can do that? I just have to do one thing. I have to do this cast, use the as keyword, sorry for that, as keyword for the casting. So let's say human as wizard, and then let's just save it. And let's see what it prints out, or which fly method it will run. Now here you can see it's running the up, or it's printing the up. Why? We have casted that run the fly method implemented on wizard. So that's pretty much easy. Instead of reading whole code or the theoretical knowledge, let's just go to the next topic. So they are implementing and then they are explaining the same concept that we have already covered. So now next topic is about the super traits. So let's say, so here, let's just comment all this stuff from here. So so super trait with the name, you can call it, let's say, the parent trait or the above all traits. So let's just go back to the documentation and get the example copied so that I can explain it to you. Let's just copy it and let's say copy it here and here. Here you can see, let's just first remove this thing from here. And now here you can see, let me just save it. Here you can see an error here. Self.toString exists for reference self, but its trait bounds were not satisfied the following trait bounds. So what does this mean? That inside that outline print, there is a method outline print, and this function does not know that the self has implemented the display trait, because toString it depends on the display trait. And then we have to implement the display trait. So we have to explicitly mention that wherever we will use this outline print trait, they might have implemented the display trait. So let's say we have to use fmt and display, and now it will remove the error, and it will consider that wherever we will use this trait, it will be the display trait will be implemented. So let's consider point example, previous example from the documentation. So let's say xi32, and let's say impl outline outline print for point, and let's say outline underscore print, and let's just pass the, let's say, um whatever you want to pass in here. So let's say pass point, or let's say pass 3. So here, let's just comment this out for now and let's just save it. And here you can see an error. The name print doesn't point doesn't implement stdfmt display. So now the Rust is saying that whenever you are implementing this trait, you have to implement the display trait. So how you can define the display trait? You have to use this like that. So for the print pretty print. So how you can implement that? You have to add the display trait inside that. So let's just go back to the documentation and then let's see what they are saying. So they have implemented this point, and then they are saying that point cannot be formatting with the default formatter, and let's just implement the display trait, and then they are saying that implementing FMT display for point, and now they are implementing the display format point. So let's say um impl format display for point, and let's add the I32 as well for y. And now here here you can see the name point is defined multiple times. Let's just go back where we have defined point. Okay, we haven't commented everything from here. Let's just comment this thing, and let's see. Now here you can see there is no error here, and every error is gone. Now using the new type pattern to implement external traits on external types. So what does this mean? So let's just really copy this code really quick. Oh, I have ran this code instead. Let's just add this code here, and add this piece of code here. Remove main function from here. Let's just save it, and let's just go back to the documentation. So here we have, let's say there is an example so let's just read out the example really quick. The theoretical knowledge, we mentioned the orphan rule that it states we are only allowed to implement a trait on a type if either the trait or the type or both are local or to our trait. It's possible to get around this restriction using the new type pattern, which involves creating a new type in a tuple strict uh, uh, tuple struct. We covered tuple structs using structs in, let's say, the tuple struct will have one field and be a thin wrapper around the type. Let's say struct wrapper tuple, and then inside that tuple we can declare right here the struct wrapper and then the vector string. So you can now, so now here you have to implement the default formatter for display format for the struct or the vector as well. So now as an example, let's say we want to implement display on vector, which the orphan rule prevents us from doing directly because the display trait and the vector t type are defined outside our trait. We can make a wrapper struct that holds an instance of vector t, and then we can implement display on wrapper and use the vector t value as shown in listing 21. And now you can print that, and hello world is printed here. The implementation of display uses self 0 to access the inner vector because the wrapper is tuple struct and vector t is the item at index in the 0 and index 0 in the tuple. Then we can use the functionality of the display trait on wrapper. The downside of using this technique is that wrapper is a new type, so it doesn't have the methods of the value it's holding. So we would have to implement all the methods of vector t directly on wrapper, such that the methods delegates to self 0. So here you can see default implementation and then self dot 0, then join, and then with the comma to separate out the implementation. So here, so this is the major point here. If we wanted the new type to have every method the inner type has implementing the deref trait on the wrapper, we have to implement the deref trait to return the inner type would be a solution. We discussed implementing the deref trait in the when we were working with the smart points. So if we didn't want the wrapper type to have all the methods of the inner type, for example, to restrict the wrapper type's behavior, we would have to implement just the method we do manually. This new type pattern is also useful when even when traits are not involved. Let's switch focus and look at some advanced ways to interact with Rust type system. So if you remember, we have already, I have shared the Rust type system guide with you, where we have all the types for the Rust. And now we are already on 118 mark, 1 hour and 18 minutes mark. So let's start with this topic. 23 or 20.3 subchapter, advanced types. The Rust type system has some features that we have so far mentioned but we haven't yet discussed. We will start by discussing new types in general. As we examine why new types are useful as types, then we will move on to type aliases, a feature similar to new types but with slightly different semantics. We will also discuss the exclamation type and dynamically sized types using the new type pattern for the. This is not pretty much this is pretty much simple concept. New types can also hide internal implementation. For example, we could use a provide a people type to a wrap hash map I32 string that stores a person's ID associated with their name. Code using people would interact. So this is the simple creating a type synonym with type aliases. So now we have type kilometers of type I32, and then so what does this mean? Now the I32 type will can be considered as kilometers, or the kilometers is the I32 type. Now the aliases kilometers is a synonym for I32. If we want to use kilometer, you can it will refer to I32. If we want to directly use I32, that's simple. Unlike the millimeters and millimeters types we created in listing 2016, kilometers is not a separate new type. Values that have the type kilometers will be treated the same as values of type I32. Mean the kilometers is not a new type. It's just a it's just aliasing or considering that I32 can be considered as kilometers in your program. Type I30 kilometers, I32 type X, I32 is equals to 5, or whether you want to pass kilometers, both will work fine. Running the code and X plus Y is equals to 10. It's fine, perfectly fine. Fixed kilometers and I32 are the of the same type. We can add values of both types and we can pass kilometers values to functions that take I32 parameters. However, using this method, we don't get the type checking benefits that we get from the new type pattern discussed earlier. In other words, if we mix up kilometers and I32 values somewhere, the compiler will not give us an error. Now, the main use case for type synonym is to reduce repetition. For example, we might have a lengthy type like this. So we can pass this type to a single type. Right here, type thunk is equals to this long type. So now you can assign the thunk everywhere, wherever you want. Type aliases are also commonly used with the result T or the value and error type for reducing repetition. Consider the stdio standard IO module in the standard library. IO operations often return a result to handle situations when operations fail to work. This library has a standard IO error struct that represents all possible IO errors. Many of the functions will be returning result enum, where the E is stdio error, which such as these functions in the right trait. So right trait, we have result use size and error. From where the error will come from the standard IO operations, and the IO. So now it's considered as the type aliases also, because instead of uh, repeating the long type declarations, we can just pass the synonym of that specific alias. Now the never type that never returns. Rust has a special type named exclamation mark that's known in type theory lingo as the empty type because it has no values. We prefer to call it the never type because it stands in the place of the return type when a function will never return. If a function will never return, never means never. If we pass, let's say, if I have a function, let's say function ABC, so this might considered as, let's say, I can uh, return something from that function, but when as soon as I add this exclamation mark, Rust will consider that I will not return anything, will never return. I will never return anything. Now here you can see mismatch type, expected types, exclamation mark, found unit type, the double. So how we can how we can remove that. So its body has no tail or return expression. Implicit returns. Now here you can see return in a function whose return type is not tuple. Return type is not a tuple. There is no return type. So how we can manage through that? So we can just here, right here. This code is read as the function bar returns never. Function that never return never are called diverging functions. We can't create values of the type exclamation mark. So bar can never possibly return. So here, let's say, where is an example? So here, our final expression that has the type exclamation mark is a loop. So loop will not return anything. So let's say, let's just quickly add move this to main function. Now here, loop indefinitely loop is used to define the simplest kind of loop supported in Rust. It runs the code inside it until code breaks. So let's just explore what's inside the loop. So this is an example of that. Let's just quickly go to the documentation. In this code, the same thing happens as in the match in listing. Rust sees the val has the type T and panic has the type exclamation mark. Means it will not return anything. The println, like, so the result of the overall match expression is T. This code works because panic doesn't produce a value. It ends the program. In the none case, we won't be returning a value from unwrap. So this code is valid. So same is that, like print exclamation mark, and so on and so forth. So like that. Dynamically sized types and this size trait. So Rust needs to know certain details about its type, such as how much space to allocate for a value of a particular type. This leaves one corner of its system a little confusing at first. The concept of dynamically sized types, sometimes referred to as DSTS, dynamically sized types, or unsized type. These types let us write code. Let's say if you have worked with TypeScript, you have the type any means, let's say there are multiple types: string, integer, number, let's say. And if you want any type, means consider whatever type would be. It's kind of a generic, so whatever type I'm passing it. But uh, if I have, let's say, dynamically sized type. So let's say I32, whether it's I32, U32, U64, U132, sorry, 128, or 256, whatever bytes. So how to define that? So let's dig into the details of a dynamically sized type called string, which we have been using throughout the book. That's right, not slice string, but stir on its own is a dynamically sized. We can't know how long the string is until runtime, meaning we can't create a variable of type stir, nor can we take an argument of type string. And Rust needs to know how much memory to allocate for any value of a particular type. So we have already discussed that value string usually stored inside the heap, and all values of a type must use the same amount of memory. If Rust allowed us to write this code, these string values need to take up the same amount of space, and so on and so forth. So this is pretty much theory. Function generic type here is actually treated as though we had written this sized. So now here, to work with dynamically sized types, Rust provides the sized trait to determine whether or not a type's size is known at compile time. This trait is automatically implemented for everything whose size is known at compile time. In addition, Rust implicitly adds a bound on size to every generic function that is a generic function definition like. So sized mm, trait will determine at the compile time. So let's say I have, let's say, pass my name. So let's say let name name is equals to Hadi, Heather, and then let's say dot to. string. And let's just save it. It's the type of string. And now, if I want to pass the type str, so how I can do that? Just remove this dot to string and let's just pass the str type explicitly. And now here you can see an error. So unreachable statement on by default, mismatch types expected str found ampersand string. So let's just pass to on found string. So it's converting dot to owned is converting it to string. So let's say express. So here let's just let me just explain it to you really quick. Um, this code not compile. So it's let me just go back to the size. So now here instead of directly passing the generic type to you, you can directly pass the function generic and the size. So let's say right here generic, and then let's say type would be, let's say, string new Hadi. Or I can also pass, let's say, Hadi. And here, comment all the things out from here. Uh, let's just comment everything from here. All right, let's just save it and let's just. All right, here you can see it does. It means that it will types with a constant size known at compile time. It will know find that it will determine the size of this parameter passed to that function at compile time. So let's just quickly, a trait bound on size means t may or may not be size at this notation. Adding a question mark operator before size, it might say to Rust that it might be or might not be or may not be the sized. Okay, and this notation overrides the default that generic types must have a known size at compile time. The trait syntax with this meaning is only available for size, not any other traits. Also, note that we switched the type of the t parameter from t and ampersand t, this reference to that generic, because the type might not be sized. We need to use it behind some kind of pointer. In this case, we have chosen our reference. Next, we will talk about functions and closures. So let's go to the next topic. So here we are on the topic advanced functions and closures. This section explores some advanced features related to functions and closures. Function pointers. We have talked about how to pass closures to functions. You can also pass regular functions to functions. This technique is useful when you want to pass a function you have already defined rather than defining a new closure. Functions coerce to the type function with a lowercase f, not to be confused with the function closure trait. So let's say we have a function add 1 x I32, simple function, nothing complex in that. We have f means a function and we are passing the argument. So let's say function, here we are getting the function whose return type is I32. So the syntax for specifying that a parameter is a function pointer is similar to that of closures, as shown in listing, where we have defined a function add1 that adds 1 to its parameter. The function do twice takes two parameters, a function pointer to any function that takes an I32 function right here and returns an I32 here, and one I32 value. The do twice function, f twice passing in the arg value, then adds the two function call results together. The main function calls do twice with the argument add once and 1 5. Add once means it's an function, it's a function, and f arg plus f arg means pass the argument. So passing it in the arg, the arg value, then adds the two function call results together. So it's perfectly fine. So f means function means what this add one, and then the let's just copy it and let's just here you can see a function is passed here. And then inside that do twice function, we have f it refers to a function, and we are passing the arg is a number, 5 is passed here inside that, and 5 here. So 5 plus 5. So 6 plus 6 should be 12. The output should be 12. The answer is 12. And this is pretty much it. Let's just go back to the documentation here. And then this code prints the answer 12 we specify, and then as an example of where you could use either a closure defined inline or a named function, let's look at a use of the map method provided by the iterator trait in the standard library. To use the map method to turn a vector of numbers into a vector of strings, we could use a closure, as in the examples here you can see list of numbers dot iterators. We can implement the iterator and the closure here dot collect. Or we could name a function as the argument to map instead of the closure. Listing shows what this would look like. And then this is pretty much it. Returning closures are represented by the traits, which means you can't return closures directly. In most cases where you might want to return a trait, you can instead use the concrete type that implements the trait as the return value of the function. However, you can't usually do that with closures because they don't have a concrete type that is returnable. You are not allowed to use the function pointer function as a return type if the closure captures any values from its scope, for example. Instead, you will normally use the impl trait syntax we learned about in chapter 10. You can return any function type using function once, function mute. Here you returns closure implementing a function i32 which is returning the i32. Now you are returning a closure here. So now x plus 1. However, so let me just run this. No output because we haven't. It's just means that it's compiling perfectly fine. However, as we noted, closure type inference and annotation, each closure is also its own distinct type. Let's say if I have a map, uh, if I am using a method, and inside that map we have a closure of type, let's say whatever type, I32, U32, and whatever. If you need to work with multiple functions that have the same signature but different implementation, you will need to use a trait object for them. Consider what happens if you write code like that shown in listing 2033. Let handlers, there are multiple return closures, return initialized. For handler in handlers, so let's just first understand, let's just copy this. As mentioned directly in the documentation, this function won't be able to compile for now. Let's just understand what they are saying. What's the inside this concept? So it returns closure. There is a closure, and then which is returning x plus 1. Returns closures initialize means init value, the initial value here, and move, we are moving, we have added the move block so that we can get the value from that x plus initial value. And let's say we have passed both the functions here, handler in handlers, and then the output handler is equals to 5x. let's just go back to the documentation. Here we have two functions, return closure and the theoretical knowledge here. And now the error message tells us whenever we return an infiltrate, Rust creates a unique opaque type, a type where we cannot see into the details of what Rust constructs for us. So even though these functions both return closures that implements the same trait, function I32 returning the I32 and the opaque types Rust generates for each are distinct. This is similar to how Rust produces different concrete types for distinct async blocks, even when they have the same output type as we saw in chapter. So now we can add the box pointer here so that we can point to that. Now, if I want to run the code, and let's try to run the code. Here, one we have the outputs 6 and 28. The handler refers to this handler, and handlers is a vector. So each function will run. So we are passing the input 5 to the handler. So let's say we have returns closure. We have what we have inside this returns closure. We have x plus 1. So means 5 plus 1 equals to 6, and then 5 plus initial value. Initial value is 123, and the 123 plus 5 is equal to 128, and the outputs is pretty much same. And then the handler refers to that. So this 5 is considered or is passed to the closure. So this 5 is accessible inside this closure. So this is pretty much simple. So let's just move on to the next topic about the macros. All right, so macros, we have used macros like println throughout this book, but we haven't fully explored what a macro is and how it works. The term macro refers to a family of features in Rust, declarative macros with macro rules, and three kinds of procedural macros. So macros are similar to functions, but there are some differences between them. So let's say function must have a specific number of parameters, let's say one parameter, two parameters, the function arguments you can say, and then the macro rules can have as many arguments as you want, and then the function and one more thing, macro rules runs another code. So let's say let's consider println. So println, so I can pass anything inside the println and as many number of arguments and as I want. I can pass the arguments as many number of. So now custom drive macros that specify these are the kinds of procedural macros. So there are two types of macros, declarative macros and procedural macros, and we are exploring the three kinds of procedural macros. Custom drive macros that specify code with the drive attribute used in on structs, and enums attribute like macros that define custom attributes usable and on any item, and function like macros that look like functions calls but operate on the tokens specified as their argument. So the difference between macros and functions, fundamentally macros are a way of writing code that writes other code, means a code writes another code. Let's just explore the what we have inside the println. Click on this println and let's just explore. So here you can see the syntax of macro. So macro underscore rules and exclamation mark and println name of the macro, and then inside that we have a parenthesis and the arm here, and then inside that block we have the create print, and inside that we have the dollar sign dollar arg and dot colon tt, and asterisk means repeat as many times there are arguments. So let's say Here we have, and one more thing, which is known as metaprogramming. Macro rules can also be called as metaprogramming. This concept is known as metaprogramming. In Appendix C, we discuss the drive attribute, which generates an implementation of various traits for you. We have also used the println and macros throughout the book, all of these concepts. So now, meta programming is useful for reducing the amount of code you have to write and maintain, which is also one of the roles of functions. However, macros have some additional powers that functions don't have. And one more thing, macro rules can become complicated and the code becomes complex when you add more and more macro rules. So our function signature must declare the number and type of parameters function has. Macros, on the other hand, can take a variable number of parameters. We can call print ln hello with one argument or two argument and whatever. The downside of the downside to implementing a macro instead of a function is that macro definitions are more complex than function definitions, because you are writing Rust code that writes Rust code. So this is the main thing. So what if, so let's say uh, we have a vector, let's say 1, 2, 3, and let's just click on this vector and see what we have inside that vector. Here you can see we have element and expression. So it's calling an expression and a vector expression, or and inside that block, so x expression, so it's saying that store the expression here inside that $x, and then add the comma after that and plus, and then the dollar comma and the question mark, and then the adding into the vector. So now another important difference between macros and functions is that you must define macros or bring them into scope before you call them in a file, as opposed to functions you can define anywhere and call anywhere. So you have passed it anywhere and you can use inside main function, whatever. Declarative macros with macro rules for general meta programming. The most widely used form of macros is in Rust is the declarative macro. These are also sometimes referred to as macros by example. So let's consider macro rules. Macros, or just plain macros at their core, declarative macros allow you to write something similar to a Rust match expression. As discussed in chapter 6, match expressions are control structures that take an expression, compare the resultant value of the expression to patterns, and then run the code associated with the matching pattern. And then this is pretty much theory. So let's skip that. And then they are explaining this macro rule for the vec macro. So here we have already explored inside the, because it, this block is not the match pattern, so it's the macro value, and it's the, there is a one arm only. So if this condition is true, then it's perfectly fine, else it will throw an error. So the actual definition of the VAC macro in the standard library includes code to pre-allocate the correct amount of memory upfront. That code is an optimization that we don't include here to make the example simpler. So we have already reviewed the complex example here. So they are explaining all these stuff. We have already covered that. Now let's look at the pattern in the body of the code associated with this arm. Temp vec.push within dollar parenthesis asterisk is generated for each part that matches dollar, and in the pattern zero or more times means asterisk means whether there is no any the values, or there are many number of values. So let's say asterisk means zero or many. And then when we call this macro 123, the code generated that replaces this macro call will be let mute temp vec एक नया vector create हो जाएगा. It will create a new vector temp vec dot push 1, 2, and 3, and then returns the temp vec. Now we have defined a macro that can take any number of arguments of any type and can generate code to create a vector containing the specified elements, and then so. So now we have procedural macros for generating code from attributes. So how we can work with that? So let's say here, just take an example here. So here we have the macro export, it's exporting the macro, rusty allow internal unstable. These are the attributes you can pass in. And one more thing, what are procedural macros? The second form of macros is the procedural macros, which acts more like a function and is a type of procedure. So procedural macros accept some code as an input, operate on that code, and produce some code as an output rather than matching against patterns and replacing the code with other code as declarative macros do. There are the three kinds of procedural macros are custom drive, attribute like, and the function like. Drive macros, this is kind of procedural macro, attribute like, and the function like, and all work in a similar fashion. So in declarative macro, we usually match over the pattern, and in the procedural macro, we work on the procedures like say pass input, work on that, and get the input. When creating procedural macros, the definitions must reside in their own crate with a special crate type. This is for complex technical reasons that we hope to eliminate in the future. And then this is pretty much it. Use proc macro and then the sum attribute and the function declaration here. How to write a custom drive macro? How you can write your custom drive macro? Let's create named hello macro that defines a trait named hello macro, and then this is pretty much it. So let's say we have created a drive and the hello macro. So to get a default implementation of the hello macro function, the default implementation will print hello macro. My name is type name, where type name is the name of type on which this trait has been defined. So let's say, for this we can create the minus minus lib, the library crate. So let's just quickly add lib.rs file, and inside that file we can inside that lib.rs file we can add a function. Let's just go copy it right now, pub trade hello macro, and then inside the main file we can directly use this. Let's just save it really quick, and let's just go back to the main file. Okay, it's becoming too long, so let's just quickly close this. Add this here. Let's just quickly add this here. Now save it really quick. Save it and save this lib.rs file, and let's just import the hello macro. It will be imported from the lecture 18 hello macro. Let's just save it really quick and let's just run what we have. So now it's printing hello macro. My name is pancakes. So how it's working? Pancakes colon colon hello macro. Inside the hello macro, what we have a print statement by my name is hello, and we have a trait hello macro function hello macro. Now, let's say, however, they would need to write the implementation for a block for each type they wanted to use with Hello Macro. We want to spare them from having to do this work. So now, if I want to create a drive macro, so how we can do that? We have to add the proc macro true is equals to true inside the lib, and then we have to add the syn and the code uh, dependency. So let's just create a new element inside the cargo.toml file. And let's just copy this for now instead of directly adding this with this command cargo add. Let's just close everything and let's say And inside that hello macro drive source lib.rs file, we can copy this function. So it is doing, proc macro drive, it's imported by the function, the project's name. Hello macro, we are passing the trait, what we have, and then the hello macro drive input whatever we want to pass it here, and explaining that. And drive input indent, call an indent, then the pancakes. So it will be considered as the dynamic input from the resultant input. And now here you can see implement hello macro, and then the, sorry for that, copy this in lib.rs file. Let's just function impl hello macro, and then the token stream. This is a simple function here, and then the hello macro. Let's just import this code. This token stream. And hello macro is a function which is print hello macro is, and this is the dynamic value which will be coming from the name hemp, and hashtag name is coming from the indent, sorry, ident. We get an ident struct instance containing the name identifier of the annotated type using the ast.ident. The struct in listing the picture shows that when we run the impl hello macro function on the code list code in, the ident we get will have the ident field with a value of pancakes. Thus, the name variable in listing 2034 will contain an ident struct. And this is the explanation of that specific code macro. And if I want to use that specific macro, how I can use that, I have to pass the path to that, to a specific macro, and then we can use it same as we usually do. So now we can add the procedural macro inside the route. We can add, let's say right here, proc macro attribute, we can pass that. And function like macros, we can add the function like macros, define macros that look like function calls. So let's say right here SQL query. So in our previous video, and when we were building the backend, so we used to pass the query similar to that. So now we can pub function SQL, and we can pass the SQL queries through the function, and it will considered as the token stream. So summary, now we have some Rust features in your toolbox that you likely won't use often, but you will know they are available in very particular circumstances. We have introduced several complex topics so that when you encounter them in error message, suggestions, or in other people's code, you will be able to recognize these concepts and syntax. Use this chapter as a reference to guide you to solutions. Next, we will put everything we have discussed throughout the book into practice and do one more project. So I would love to add some examples for the macros in our next videos, and the about the advanced features. And that's pretty much it from today's video. So this video has a lot of concepts, the advanced concepts, and um, I'm pretty sure y- some concept didn't make sense for you for now. So as soon as we get hands-on on these concepts, you will be fluent in that. So that's pretty much it. If you have anything, if you have any queries, any feedback, just drop it in YouTube's comment box, or you can share with me on my socials. If you haven't subscribed my channel yet, you can subscribe it. If you haven't followed me on my socials, especially on LinkedIn, X, and Threads, you can do so, so that you can get the um, knowledge from the theoretical knowledge and the deep concepts, deep concepts about the concept that we have learned in the from the documentation. And that's pretty much it. If you have any feedback about any video related thing, or if you have built something and you have learned anything from my video, just share it with me. I would love to bring that in the video so that others can get more motivated and continue with this journey, because we know that the learning curve is quite steep, and but it's quite rewarding at the end. So yeah, that's pretty much it, and I hope you have learned a lot of stuff from this video. And if you have learned a lot of stuff from this video or anything, just give a thumbs up and subscribe to my channel. So that's pretty much it. Till the next video, bye, be safe, be productive.